where we stopped at the previous video for the machine learning classification using logistic regression and generation of random data, we stopped at the features, the generation of the features. So this is the code for that. Features f is equals to for f in data df if the feature is in the data is in f. So it's going to generate. It just collects all these features from feature 1 to feature 10. So if you check it, features, you check that. So it's going to be from feature 1 to feature 10. And so we want to separate our data. The data is 5,000 points, but we want to have the training data and the test data. So for the training data, so the first 4,000 rows for the training data, and then for the test data, the last 1,000 rows. We are reading it from the tail to the last 1,000 rows. That's why we used tail. This one used head. Head means starting from the beginning down to 4,000, but tail is starting from the below upwards to 1,000. So this is our test data and our training data. So we want to collect our x and then our y value. So for the training data, collect all the features in the training data, like we mentioned, feature 1 to feature 10. That's what it does here. And then for our y, is going to be for the target data. And then we are going to use the train test split to split our data. So our training data set has to still be splitted. So we have our test data set and we also have our training data set. The training data set has to be splitted to in 70-30. The 70 for the training of the model, the 30 is for the validation of the model to see if it does not generalize. After the validation, we will now use the model for the testing data set. So that's what we want to do now. We have the x train, x test, y train, and the y test. So we have for our values x and then y, and then for the test size, so the test size we are using is 0.3, which means 70% should be for the training data, and then 30% will be for the validation. So there's a validation. So we have the training data, we have the validation data to validate the model to see how well the model does. And the random state is just to keep, so there should not be a lot of reshuffling in the data. So there should be a little bit of consistency. That's why we're using the random state. So random state 1.123. Then if you check very well, our length of the x tree and length of the y tree, they are fairly the same thing. So it's actually 2,800, roughly 70% of 4,000. And then for the testing data set, our test, which is actually the validation, is 1,200, so 0.3% of 4,000. So we call our model. Our model is the logistic regression model. That's what we're going to make use of. We just want to make it simple. We don't want to start putting the parameters. For example, if we write the model now, so we have the parameters in the model. So for example, if you write help of the model, so it shows you it's actually logistic regression. So they have the penalty L1, L2. The penalty is to penalize the model if it doesn't perform very well. And how for the regularization, the inverse of regularization C. So you have the intercept. These are the parameters or the arguments for the model. But that's not what we don't want to start making it complex. So we just use the model as it is, and then we are going to fit the model to fit using our data set, the training 70%. Remember, the 70% of the data set, the model training has already been trained, and then we make our predictions. The predictions using the test value of the 70%. So this prediction has been done. So our predicted value is this. Let's see the first 10 rows of the predicted value. So 101010 1101. But we want to know how good is our model. So you have the matrix for measuring how good our model is. But one of the matrices is accuracy. Another one is mean squared error. Another one mean absolute error. Accuracy should be, if it tends towards closer to 100, the better. But sometimes the matrix of accuracy may not work. It may not give us the value we want it to give us. So, for example, if you have a skewed data set, so for example, in fraud detection data set where you have a larger portion of the normal transactions. Normal transactions are on the larger portion, so close to 97%. And then the fraudulent transactions are close to 3%, for example. If you use the model for accuracy, it will give you roughly 97%. You think that the data set is good, that it's accurate, without knowing that it's generalizing towards it's skewed. The data set is skewed. So that's why most times the model for accuracy will not really give us what we want. That's why we can make use of other metrics like the F1 score or the ROC. But that's for another tutorial. So, but let us just use the accuracy score. So this is the accuracy score for the Y project and the Y test. The accuracy is really good, 99.8, close to 100. So it almost generalized to the data. So if we can just check it, Y period, to see how much close this is the Y period, the first 10 values of the Y period, and Y test is the test row of our validation. So we have the validation data, it has the Y test. Let's make it in NumPy array to be able to see it to X test. No, that's not what I just did now. I just made a mistake. So Y test, the first 10 rows of the Y test, and then Y prediction. Just making so this first 10 rows of the Y test and the first 10 rows of the Y prediction. So it's almost close, almost 1 1. So the one in the Y test is 1, the first row is 1, and this one predicted it very well. 1 is 0 here, predicted 0 is 1, it predicted 1, 0 predicted 0, 1 it predicted 1, 0. So almost the first 10 rows are, it cuts the first 10 rows. So that's why the accuracy is really good. So the mean squared error is another kind of matrix for matrix to measure how good our model is. And for mean squared error is what is the distance between the prediction and the real value. If the distances are close, almost close to 0, it means it's very good. It means it fits very well with the data. So let us see what it's going to give us. So the mean squared error. We're going to compare it with the Y prediction and the Y test. Wow. 0.0016. It's almost close to 0, which is really good. So it is good with the model generalized very well with the validation data. So now this is the period we are going to use the model on a new data set, which is the X test. The testing our test data set. So we have our test data. Our test data. So we want to predict with the model. Our prediction for the model. XPredict. So you go to model.predict. So the features from the test data. So it has predicted. And this is our test target. The column 4. So this is in our test data. Remember, it was the 1000 part of the data. So you have the 4000, which was used for the training, and then the 1000 is for the testing. This is this one. So it has its own column. We want to see if this test prediction is close, is almost the same with the test target. So this is our test target. So look at our test prediction. So okay, our test prediction, the predicted data. We want to see the first 10 values of it. Or let's say the first 20 values of it. And then let us check the test target, the one that the data came with, to see how close is it with the predicted version. The first 10 rows, or the first 20 rows. Let's put it in numpy.array. So it's almost everything. They predicted almost everything the same. So it's a very good model for this data set. Almost everything is predicted. There is no error even in this. So check our accuracy score. For the accuracy score will be for our test prediction. Our test prediction and test targets. .999 is good. Our mean absolute error, mean squared error, but it's for the test prediction and the test targets. Is it close to 0? Let's see. Almost close to 0. And then mean absolute error. This one is also another metric for testing how good our model is. So it's supposed to come close to 0. Close to 0. So the summary of what we did now is that, first of all, we generated our data. Let's see. We imported the functions that we want to make use of. We generated the random data, and then we rearranged the data. We rearranged it to 10 rows and 5,000, 10 columns and 5,000 rows. We summed the data to create our sum column, and then the target. We created the target from the sum, and then we renamed our features. And after renaming, we split our training data set to 70-30. We generated the model, the logistic model, and then we fit the model with our training data, and then we validated it with the validation data set, and then we ran our predictions on test data and checked our accuracy, and our accuracy is good. So this is just a basic introduction to machine learning using logistic regression. It's a classification problem to classify whether it is zeros and ones. We're using the model, the simple model, logistic regression. So in subsequent videos, we can elaborate on other kinds of machine learning models, and then work on maybe generated data, a random generated data, or real data sets to give an insight into the wonderful field of machine learning and deep learning.